In the previous video, we discussed that we want to build an expectation maximization algorithm for this simple discrete probabilistic fitting problem. And we finished the E step, which is summarized in the bottom of this desk. So now let's go ahead and proceed with the M step. So on the M step, we want to maximize the expected value, maximize with respect to the parameters, so in this case alpha, beta and gamma, of the sum of, with respect to the objects in the dataset, of expected values with respect to Q of Ti, of joint distributions, logarithms of the joint P of Ti and Xi, which we can rewrite as a product of P of Xi given Ti times, and again given the parameters, but I will omit them everywhere, times the prior P of Ti. And we can rewrite this thing by using the definition of the expected value, which is sum with respect to all possible values for Ti. And there are two possible values for Ti here, so it will be sum. The first term will be corresponding to Ti equals 1. So for data points that are coming from the first component of the mixture, here will be logarithm. Here will be the weight, the probability Ti equals 1, times the logarithm of Xi given Ti equals 1 times the prior. And the prior here is just gamma, so probability of Ti equals 1. Plus the second term, which is the same thing but for Ti equals to 1. So again, sum with respect to all the objects in the dataset, the variational distribution Q, Ti equals 2, times the logarithm of the joint distribution, which is logarithm of P of Xi given Ti equals 2 is just P of P2 of Xi, and times the prior, which is 1 minus gamma. And we want to maximize this thing with respect to parameters, so with respect to alpha, beta and gamma. Let's rewrite this expression by using the definition of Q, using the one we derived on the E step, and also substituting the definition of P1 and P2. So here we will get something like this. Oh, let's to start with, let's make more concrete which data we have. So let's say that we observed 30 objects equals to 30 Xi equals to 1, so N1 equals to 30. It's a number of observations Xi which are equal to 1, N2 equals to 20, and N3 equals to 60. So this is the complete definition of our dataset. We have 30 ones and etc. And now we can proceed with this fitting algorithm. So now we're going to write this thing, and instead of writing everywhere sum with respect to objects, let's decompose this thing into three terms. First of them corresponding to the Xi is equal to 1 and etc. So the first term will be, there will be 30 terms equal to each other. That corresponds to the Xi's that are equal to 1, right? And so Q of Ti equal 1, in this case, will be just P of Ti equal 1, given that Xi equal 1. So it's the terms corresponding to Xi equal 1, right? And this thing is just 1, if we look up our results from the E step. This is 1, and times the logarithm of the joint distribution. So logarithm of P1 of 1, which is alpha, times the prior, which is gamma. So probability that T1 equals to 1 is the first term of the first term here. The second term will correspond to Xi is equal to 2, so there will be 20 of them. The probability of Q of Chi in this case will be 0.5 from here, so it will be times 0.5 times logarithm of the joint distribution, which is 1 minus alpha times the prior. It's P1 of 2 plus the third term, which is, so there will be 60 xi is equals to 3, and the probability, this Q of Ti will be 0. So this will be 0 times logarithm of also 0, which may look like a problem, but actually it's usually considered that 0 times logarithm of 0 is 0. So even if you do it carefully, it will be okay. You just can ignore this term in maximization problem. So this thing is ignored because it's 0. Plus the terms corresponding to this part. So plus the terms corresponding to the xi's that came from the second component of the mixture. Again, there will be 30 xi's equal to 1 times the prior times the variational probability Q of Ti equals 1. And this thing will be P of Ti equal to 2, so second component of the mixture, given xi is 1. And this is 0, right? So we assume that no ones can came from the second component of the mixture. So again, it will times logarithm of 0, but anyway, we ignore this part. This is 0. And plus the final two terms, which is 20 times 0.5, which is Q, times logarithm of 1 minus beta times 1 minus alpha, or 1 minus gamma, which is prior probability for the second component of the mixture. And this last term is 60 times 1 times logarithm of beta times the prior probability for the second component, which is 1 minus gamma. So finally we have this expression, and we want to maximize it with respect to alpha, beta, and gamma. So let's try to simplify it a little bit. So get rid of the zeros and things like that that can make things harder for us. And also move all the parts that it depends on the same parameter together. So let's start with maximizing with respect to alpha, for example. Let's identify the terms that depend on alpha. So this thing will equal to so this part does depend on alpha. It will be 30 times logarithm of alpha plus 30 times logarithm of gamma, but we don't care about it because it's a constant with respect to alpha. And now we want to maximize with respect to alpha. So plus 10 times logarithm of 1 minus alpha. And there are no alphas anywhere else. So plus constant with respect to alpha. And we want to maximize this expression. How can we do it? Well, let's take the gradient and set it to 0, as usually. So the gradient of this expression with respect to alpha will be 30 times gradient of logarithm of alpha, which is 1 divided by alpha, plus 10 times logarithm of the gradient of logarithm of 1 minus alpha. It's 1 divided by 1 minus alpha times minus 1. And this thing equals to 0. And finally, we can solve this equation by just writing down this ratio. So 30 divided by alpha equals to 10 divided by 1 minus alpha. and by multiplying each part by 1 minus alpha and alpha, we can get that, well, 30 minus 30 alpha equals to 10 alpha. And finally, which means that alpha equals to 30 divided by 40. So we found our alpha after the M step. So we updated the parameters of our latent variable model. We started from the initialization alpha equals beta equals gamma equals 0.5, and after one step of the expectation maximization algorithm, alpha started to be 3 divided by 4. So we can solve the same optimization problem with respect to beta and gamma and get the following numbers. So beta will be 6 divided by 7 and gamma will be 4 divided by 11. So we found our parameters, and actually it turns out that if you repeat this expectation maximization steps a few more times, you will not update the parameters anymore. So we have already converged after one iteration of expectation maximization. And these parameters kind of make sense. So they say that the first component of the mixture mostly focus on generating ones. So the probability of generating 1 is 3 divided by 4. It's larger than 0.5. And the second component of the mixture focuses on generating number of threes. And we're a little bit less influence of the first component than of the second one, because there are less ones than threes. So thus we considered in details this one step of the expectation maximization algorithm for a discrete mixture model.